math based on this, okay? So if you send a charged particle into an electric field and you send it into a uniform electric field, right? We find that the charged particle will go forwards, but there's a force acting downwards. So it'll also move downwards. And as a consequence of going forwards and moving downwards, it creates a projectile, a parabola, right? So if you look at the velocity individually, you'll find the horizontal velocity should remain what throughout? Constant, because there's no horizontal force action on the system. However, because there's an electric field that's like that, your velocity will start to increase. And that's because there's a constant acceleration being provided here, okay? So that's the reason why it undergoes a parabolic path. Now, unlike projectiles, where we saw that, like AS projectiles, we saw that mass didn't have an impact. Here, mass does have an impact. So if they ask you a question, why does mass have an impact? What would your answer be? Like, why does mass actually change the path? Because we previously learned mass didn't change the path. By the way, I mean, mass will drop with the Islam. Can you tell me, would 2m go further out or closer in? Yes, very good. So it'll go further out. And the smaller the mass, the closer it will be. So what's the reason? Can anyone explain that to me? Why is it that the path changes because of mass? Because we learned in our gravitational field chapter, right, like AS projectiles, mass didn't have a factor. So why does mass now have a factor? Yeah, so unlike gravitational field, in an electric field, mass change will cause what change? Acceleration change. But in a gravitational field, if you're a light object, heavy object, any object, what is the acceleration? 9.81, right? So because the mass causes an acceleration change, the path will also change as well. And the one with the smaller mass, right, will have a higher acceleration. Therefore, it'll go down very rapidly. So it'll hit the surface much earlier, right? The one that's very heavy will require more effort to go down, right? So it goes and hits farther away. Clear. Also, we found that there's another factor that plays a role. What is that? Charge. So how does charge impact your path? More charge means more force. More force means it'll bend easily. So the higher charge here will bend more rapidly. The less charge will bend less rapidly. Is it okay? Right. So that's it. And the thing that you have to be very careful about is that whenever you're finding acceleration, you have to take into account what and what together. Charge and mass, okay, because both of them have their roles to play. Also, they don't have the same role that they play. One of them is directly proportional, the other one is inversely proportional. So you have to take that into account and figure out what's happening here. So anyways, we will do a couple of questions from this, and then we will move on to non-uniform field today. All right, so I take examples. See, this one example is enough, actually. It's a very elaborate example. Okay, it says proton enters the field horizontally there. Find whether the proton remains inside the field or leaves the field. It enters 2.5 centimeter mark vertically. So it enters at this location here. It's a proton going there. It's entering at 5 into 10 to the power 5 meter per second. You need to do your math and figure out, does it stay inside or does it go outside? That's it. Okay, this is you'll find this in the AS paper. It used to be very popular in the electric field topic that we had in AS. So yeah, give it a try. Mass of a proton is something that you need to know. So mass of proton is 1.67 into 10 to the power minus 27 kilogram, and the charge of a proton is 1.6 into 10 to the power minus 19 coulomb. Did you understand the question? So you have your particle entering at 2.5 centimeter location in the field at a velocity of 510 meter per second. Now it could do this, it could do that, right? You have to figure out using math, what does it do actually? Does it stay inside or does it go outside? Right. Just uniform টা জন্য non-uniform টা আবার এইটুকুই আছে। না, extra class তো extra class এসে করতে হবে। Today is an extra class, I think I told you, right? The extended class. So it's going to be on, if you have school exams, you can clarify your problems. Yeah, 10 centimeters is the length of the plate at the bottom. So for a starter, you need to find acceleration. That is the first part. Okay, acceleration of it. And the next part is like a projectile motion question. Stays inside. How did you conclude that? Range. That's okay. And the range is less than 10. What's your acceleration? Acceleration. Josh. Okay. Okay, let's first find the acceleration. But acceleration target, right? So how do we find acceleration in this case? So acceleration no. What we need to do here is F by Q equals to V by D. The force here is mass into acceleration. So mass into acceleration divided by charge equals to V by D. Now we need to substitute whatever we know, right? So the mass is 1.67 into 10 to the power minus 27 times acceleration divided by what is the charge? 1.6 into 10 to the power minus 19 equals to V is the potential difference. How much is it? 10,000, correct? So 10,000 divided by the separation of the plates, or 2.5. Yeah, it should be 4 centimeter, not 2.5, because the field is not generated because of where your charge is. The field is generated because of how far the plates are. So that's why you always take the plate separation here. That's 4 centimeters. So 4 divided by 100. So yeah, you get an acceleration. How much? 2.395. 13. That's okay. 13 meter per second squared. That's your acceleration. Now, how do we come to the answer though? Because the question is asking you, does it stay inside or does it go outside? And this is a mechanics question. So how do you conclude whether it stays inside or goes outside? There are many ways of doing this. One of the ways, the one I prefer, is to find the range. So what you do is you find the range of the particle. What's range? Range is how far does it go horizontally? And if your range is more than 10, right, what does that mean? Yeah, it goes outside. So let's say this object has a range of 20 centimeter. It'll be somewhere there, right? But if the range is like 5 centimeter, wouldn't it go inside? Right? So what we do is we find the range of this particle. So range টা বের করার জন্য যে ম্যাথটা করতে হবে, it's like solely a what math? Mechanics projectile math, right? So how do you find range? So I've given you a formula, ASA. Do you remember what that was for range? Yeah. So range is equal to horizontal velocity into time of flight. Okay, so the time of flight, or whichever way you want to find range, it's up to you. So we need to find what here now? Time of flight. Time of flight key. The time taken for the particle to hit the plate, right? How do you find that time? Right. S equals to, so firstly we need to find time. S equals to ut plus half at square. S is going to be the distance fallen, so 2.5 divided by 100 equals to U is going to be my initial velocity vertically, which happens to be what in this case? 0, because it's going straight, so it's just 0 there. So 0 into t plus half times that acceleration, 2.395 into 10 to the power 13 times t square. So by doing this math, you'll find the time of flight is going to be like really small number. How much is it? 4.569 minus 8. Right. So that's the time taken by the particle to go and hit the plates. But if you remember from your AS, right, the time needed for the particle to go straight down like that, go that way, go that way, go that way, all of these are the same. Why? Because what brings the particle down? The acceleration, right? And the acceleration is same for all of them. The height fallen is also same for all of them, right? So we can use that to find the range. So range is now going to be the horizontal velocity, which is 5 into 10 to the power 5 into 4.569 into 10 to the power minus 8. Is the initial velocity the initial horizontal velocity? Initial velocity? No. This is the vertical velocity, because we are doing vertical motion, right? Vertical initial v is equal to 0. Yep. So that will give your answer. So how much is the range going to be here? 0.0228 meters. Yes. Okay. Or because it's in centimeters, so 0.228 centimeters, which is definitely not more than 10, right? So what does the particle do? Sorry. So yeah, it's still less than how much? 10 centimeters. So because it's less than 10 centimeters, what does that mean? It stays inside. Okay. Some students try to do this in another way, which I don't really personally recommend, because I don't think it's intuitive. They use time and they compare time. So they find the time needed for the particle to go and hit that place. So they'll use this range and find the time, and they'll find like where does the particle go and hit. So if the particle goes and hits above that point, it goes outside. If the particle goes and hits below that point, it stays inside. which I don't think is easy to understand. Range is much more easier, okay? So I think it's a number you need to compare with. If your value for range is less than this, it stays inside. If your range is more than 10, it goes outside. So in this particular question, it does go outside, okay? That's very good. So that is it. This is the most complicated you can get. So conclusion would be, since range is less than 10 centimeters, it stays inside. Clear? Okay, so we are done with uniform electric field. It's a small topic, but it's standalone and different from what we can do right now. So just go back to the syllabus and check if we have covered everything. It was added in 2022. So understand that electric field as an example of a force and define electric field as force per unit positive charge. We have done that. Recall that F equals to QE, which is E equals to F by Q, right? So the formula. Represent electric field by means of field lines. We have done that as well. Okay, so that's the first part. Then I think it out uniform. Recall and use E equals to del V by del D to calculate the field strength for uniform field between charged parallel plates. We have done that. There's one small thing left. I'll do that right now. Describe the effect of uniform electric field on motion of charged particle. This is their way of saying what motion, projectile motion. Okay, so basically how projectile motion type questions would show up will be based on this point. So yeah, we have the rest to ask, but before that, there's an issue that they sometimes bring up. Or to clarify, Corey. This one is regarding the distance and the voltage and something called equipotential lines, which will be seen in a bit. So what is this equipotential line? We have done this. Does anyone remember what is equipotential line in gravitational field chapter? No. What's an equipotential line? They have same potential in that line. What's the potential? Yeah, so it's the amount of energy per unit mass. Yes, very good. Yeah, you're right. So equipotential lines are essentially lines in fields along which there is no work done with the field or against the field. So let me show you what it means. So this is the Earth, for example. The Earth has equipotential lines around it, and these lines are like that. They're actually the other way around, not like field lines. And what does it mean is that if you go along this line, like this, there's no work done with the field, there's no work done against the field. It's like, if I take the calculator here, it has a GP of 100 joules, right? If I go left, how much is the GP? 100. If I go right, 100. So, if I keep going left and right, the GP remains the same. So there's actually an invisible line here called the equipotential line. So if you move along the equipotential line, you don't need to do any work because you're not doing anything against the field or with the field. And that's what the satellites are. The satellites keep going along the equipotential line, so they don't need any engine. They can just keep going along. But sometimes they would want to go away or towards. In that case, the equipotential lines will play a role. So if you want to come closer to the Earth in gravitational field I'm talking about, do you lose energy or do you gain potential energy? You lose, right? And the loss in potential energy is converted to what energy? Kinetic energy. On the other hand, if you want to go out from the potential to a further location away, you need to gain what? Potential energy. And that can only take place if you are provided with external energy such as what? K. And that's how you throw a ball up in the air and it goes to a new potential, right? So yeah, these are called equipotential lines. Also, does anyone remember that these lines had a meaning in terms of their separation? When the separation meant something. Can anyone remind me what they meant? Yeah, so let me show you what I'm trying to say here. This separation here and that separation there, how do they relate in terms of energy change? Energy change is the same for the green part and the red part. Yes. Okay. So equipotential lines যখন draw করা হয়, the separation between any two equipotential line represents same change in energy. So if an object goes from here to there, it's going to gain 50 joules. If it goes from here to there, it will still gain how much? 50 joules, right? So then why is this a separation different? So it's visibly bigger, right? So it is meant to be like that. Why? Yes, so the further you go, the strength decreases. And if you use the basic idea of mechanics, work done is equal to what? Force into distance, right? If you go further away from a planet, isn't the force getting weaker? So to do the same amount of work, what distance do you need to travel? Greater, right? So that's why the further you go, you'll find these lines are getting spread out. And they're getting spread out because for the same amount of work, right? Now you need to travel further because what is getting weaker? The force. So this is called equipotential line. We have this in charges, okay? Charges are back forward. But what about a uniform field? How does the equipotential lines have or look like in a uniform field? So let's say this is, I'll give numbers, plus 1000 volts. And this one is connected to the ground, earth, so 0, right? Will there be a potential or a field between these two plates? Yes, definitely, because there's a potential difference out there, right? Now, my question for you is, how should I draw the potential lines here? Should they go like this? Should they go some other way? So equipotential line is a line along which, right, if you move, there's no work done with the field or no work done against the field. Yeah, it should be horizontal line, right? So it should be like that. But my next question for you is, are the lines going to be equally spaced, or do you think they'll start to get further and further away or get closer and closer? Very good, equally spaced. Why should they be equally spaced? Because in a uniform field, the force is constant. So to do the same amount of work, what amount of distance do you need to travel? Same. So yeah, this is how the diagram looks like. Now, remember I told you that we need to take potential difference and separation of the plates. I'm going to teach you why is that. So see what I'm going to do right now. This is 1000 volts, right? And there are lines that are equally dividing your voltage here. Can you tell me what should the values be for the lines here? How do you equally divide 1000 into these many lines? 200 or 250? 250. So 750, 500, 250, 0, and then what? Yeah, it's 200, right? So I'm going to gap the So this is going to be 800 volts. This is going to be 600 volts. This is going to be 400 volts. This is going to be 200 volts and 0, right? Now, remember I told you that we take the plate separation, not the location of the charge. So I'll show you something here. Let's say this is 1000 centimeter. For clarity, I'm keeping same number. So 1000 volts, 1000 centimeter, which means that at this particular location, what should the length be? 800 centimeter. At that particular location, what should the length be? 600 centimeter. So if you find the ratio of the voltage to the distance, you'll find that for any location, the ratio of the voltage to the distance is always going to be what? Same. I'll give you a numerical example. What is the ratio of my full potential difference to the full distance? 1. So 1 volt per centimeter. What is the ratio of this 800 to that 800? 1. Every single location you go here, this ratio of voltage by distance is going to remain what? Same. And that voltage by distance, V by D, eventually we realize is the value of what? The electric field strength, which is what everywhere? Same. So that's why when you decide, some of you do this, that you take the full voltage, but tomar charge charge distance do you get the right ratio? No, right? Because aren't you taking the full potential and some middle distance? So, sometimes students will say, when can I take this distance? If you knew the what at that location. the potential difference. Okay, and then you can do that. They will give you questions. I've seen questions in AS MCQ. You don't have MCQs anymore, where they'll give you this voltage and that distance, and they'll ask you to find the electric field strength. Because it's a uniform field, what can you apply here? Unitary method. Okay, so like for example, if this distance gives me this potential, then that distance will give me that potential, and that distance will give me that potential, because they're all linearly related, right? And that's what you'll find in the, again, I'm coming back to why I brought up this thing. In the syllabus, they give the equation for field strength as what? Not V by D. Do you recall, teacher? Yes, it was del V by del D, which is the fact that any change and its corresponding distance change should always remain what in a uniform electric field? Constant. Okay, so that's why the del thing is important. Right, so I'll just add a small note on this. We are done with uniform field, so we'll now start the non-uniform field. It's 24 low. It's a 28 this day. It's actually warmer than outside. It says 27 outside. Now try করে because সম্ভব না তো, because যখন 16 হওয়ার চেষ্টা করে by the time বাতাসটা বাইরে থেকে এসে গরম করে দিচ্ছে, lowest you can get 20. বাংলাদেশে 20 নিচে যাওয়া যায় না, so 18 দিয়ে রাখলে it's always going to be 20. I mean winter পারবা, winter it can actually go even lower. Okay, so the point that I made, line below. Right, the horizontal lines are called equipotential line. They represent a line along which if you move, you're not going to gain any energy or lose any energy. Why is that so? Because what's the formula for work done? Force into distance moved in the direction of the force, right? Whenever a charged particle is placed anywhere in an electric field as uniform, the force is always acting which way? Down, like that. So if you move sideways here, there's no work done by your force. So therefore, you're not gaining any energy, neither are you losing any energy. And since the potential, the energy is the same throughout, we call it equipotential line. Right, so non-uniform field, the first thing you need to know, we have done this before, so I will just go through this. Charge approximation, yes. Okay. What's charge approximation? Karo ki jana ache? Point charge approximation, what was it? So we have done the same thing for gravitational field, where we have considered masses, right, like stars, to be what? Points. Justify that for me. Well, how is that even allowed? Because it's a star that you're deciding to consider it as a point. Yeah. So what we do is we consider masses, right, that are in space. They're obviously very big, but they're also equally what from each other, far from each other. So if you look from the point of view of the scale of distance between them and their size, right, their size is actually what compared to the distance between them, very negligible. Therefore, we can approximate the whole star to be a point, and it'll have the same impact. Same goes with your charges here as well. So for charges, obviously charges have shapes, right? Like a proton and an electron. Do you know what the shape of a proton or electron is? Sphere. Acha. Does anyone else have any other opinion? String. No, that's like inside the quartz. But what's the show? Yes, online and also you have the right answer. We don't know. We don't know what a proton looks like. A proton could look like anything, right? So why do we take them as spherical? Because it turns out when things naturally form in the universe, they tend to take the shape of a sphere because it's equal distance from every side. It's the most stable form you can get, right? So we can't see protons, as you know. We can't see electrons either. Absolutely not. So how do we know they're spheres? We make assumptions, right? Now, if you go online, you'll find pictures of atoms and pictures of protons, in fact, right? Those are actually not pictures of protons or atoms. They're picture of their field around them. So yeah, I think do you know how Braille works? Braille. Blind people read version, or they have this thing where they're dots and they can touch the dots and read, right? We get a Braille version of an atom. So basically, we can't see the atom, but we can feel the what around the atom, the electric field. And that electric field looks like there must be a what inside, a sphere. That's our judgment to why it's a sphere. But there's no picture of an atom that looks like a sphere. We don't know what it is. It could be molding around for like what we know, right? So it change korte pare. So yeah, since we don't know anything, that's what the bottom line is. We assume them to be what? A point. And a point is actually better than assuming them to be something wrong. So point can consider kora hoy charge gulo ke, so that you don't need to worry about what dimension they have, what radius they have, are they a sphere, are they not a sphere. Pointer advantage key, point approximates everything to literally a place with no dimension, but it has all the properties though. So it will have the charge, it will have the mass, it will only not have one thing. What is it? Size. Okay, so point doesn't have a radius, the point doesn't have a volume, the point doesn't have an area, but it has mass, it has charge, it has field. Okay, so yeah, it's called the point charge approximation. So amar jodi sphere use kora hoito, and we have drawn this diagram before, field to draw kora hoito, and the field would be based on the structure of a sphere. But let's say you don't take it as a sphere, you consider it to be a point. This is how it looks like. So we are done with this part. This is the diagram of your what? Non-uniform field around a point charge. And you guys are lucky that the syllabus only deals with point charges. Okay, as you do further studies in electronics charges, right, you will start to find shapes, right, that don't exist in math. But you have to create those shapes. So ogular formula ki hobe? Ogular formula tomake banate hobe. Like you have to make your own formula. So a simple example would be, amra ekta chapter korbo in the future. It's called a capacitor. So capacitor is this plate যেখানে charge store করা হয়. A very common shape of a capacitor is a cylinder. এরকম দেখতে. Now you want to find the electric field around this cylinder. None of the formula that we work will work, and you can't just say it's a point because it's actually there, right? So you can't just say it's a point. We know it's a cylinder. So how do you find its electric field? You actually have to derive a formula yourself. So there's a law out there that allows you to do so. Now a cylinder right? If I strip off the side, what shape would that be? A rectangle. You know that? Because if I cut it off and roll it out, it will be a rectangle plus how many circles on the other side? 2 circles, right? So based on the shape of a circle and a rectangle, you derive the equation for the field around it. So we are lucky that we are only dealing with something that has no shape, no size, right? So that's why our diagrams are just always going to look like this. So yeah, that's the first thing that we have. I'll cut to the chase because a topic rest of the stuff gravitational field actually correspond. So how do you find the strength of your field here? So এখানে যে ফিল্ড আছে এটা স্ট্রেংথটা কেমনে বের করব সো এটা বের করার আগে I'll introduce a law to you. So the law that we're going to learn here is the counterpart of the Newton's gravitational law. And I'll keep reminding you of the gravitational field topic because these are parallels. They're exactly the same thing. Instead of mass, what do we have here? Charge. So if you can remember gravitational field, you'll find this chapter is very manageable. Okay. So can anyone remind me what was Newton's law of gravitation? Yes, Newton's law of gravitation states that the force of attraction between any two masses is directly proportional to the product of the masses and inversely proportional to the square of their distance separation. Do you remember that? So yeah, similarly, around that time, another physicist came up with a law for charges, and the law is called the Coulomb's law. So Coulomb came up with it. So what is Coulomb's law? Coulomb's law states that force is directly proportional to the product of mass, not this time, the product of what? Charge, Q1, Q2, and inversely proportional to the what? Distance square, separation distance square. Okay, so the radius of that. So F is directly proportional to Q1, Q2 divided by D square. And this is something you learned in your O level with charges, that if you bring charges closer, force increases. If you go further away, force decreases. If one charge is more, one charge is less, what happens? The force increases, decreases. So based on that, let's go back to the time when they actually discovered this. So they found something interesting, which is this. You have one sphere, which is charged. Okay, let's say this is positively charged. And you place another sphere next to it, hanging from a very thin string. Okay, both of these are what charges? Positive charges. What will they do to each other? Yeah, so it turns out like charges repel, and that's what we found. But we also found that unlike charges, what? Attract. So the first difference, in fact, the major difference between gravitational field and electric field is that electric field is both attractive and repulsive. But it's difficult for humans to comprehend two things at once. It's just how we are, right? So what decide course is that they will only deal with what charges to come up with the equation. Positive charges. Remember, I talked about this. So all our equations are always going to be based on the assumption that all the charges that we're dealing with are what charge? Positive charge. If it's a negative charge in there, the answer would be just what? Opposite. Okay. So if there are two positive charges like this, let's say the charge here is Q and the charge here is Q, identical sphere, they'll repel each other. And as they repel each other, what you'll notice is that, right. So as they repel each other, you'll find that the spheres go to the side. So it'll go like this, and that will go like that. Do you agree? Acha. এখন, I have a question for you. How would the separation look like if I had 4Q and Q? So one of them is a charge of same thing, right? Just more charged, 4Q. The other one is Q. Do you think that the charges here would do this, which is the 4Q is so strong in its repulsion that it will repel the lower charge all the way out like that? Or do you think that the 4Q itself will experience a very large repulsion and go all the way out, and the other one will just remain where it is? Or anything else that you think? So konta hobe? Will it be the same as before? Will it be that the 4 pushes the small one out? So this is 4Q. This is Q. Or do you think the 4Q itself will move out and the Q will remain where it is? Or they're all anything. Acha. So yeah, you guys got it. So you're saying that it hobe, like both of them will move away together, even though this is 4Q and this is Q. So what do you guys feel? I'll give you options. So this is A, B, C, D. What do you think is the outcome for this interaction? Okay, how many of you think it's D? So what happened to that table? Disagree karo keno? What do you think is the answer? B. Acha. Right. So, a little surprised, but yeah, the answer is D. It is D, and the reason behind that is, what's the reason? যেহেতু তোমরা ভালোই confidence না বলছো, হ্যাঁ, identical mass but charge different না. Product. Yes. So the answer is actually much straightforward. That is true. Newton's third law. Newton's third law states that when something applies a force on something else will apply what force on the other thing? Equal and opposite, right? Hey, eventually we understand that, you know, Coulomb's law and everything comes into play, but Newton's law holds true for everything and anything. So both of them will move like that. The things that you guys thought earlier would have happened if they had different masses. তখন হচ্ছে same force, the heavy one can't go, but the lighter one will move very easily. But when it comes to same masses, right, the force is the same between them. And this force, they call it the mutual force because it's both here, but it's basically based on what law? Newton's third law there. So yes, the force is always going to be same on the charges, regardless of what amount of charge they have. And that is evident, as he mentioned, from the equation itself, that the force depends on not one charge or the other, but what together, both of them together. Okay, so yeah, this is the Coulomb's law. I'll write it down in a minute, but it's still incomplete. Why? Because the gravitational law we learned was what? F equals to g mm by d squared. So there was a constant g that was not known for many years, and that was like a barrier in our understanding. Eventually, Henry Cavendish came up with an experiment to find it, and then g বের করার পরে everything made sense, right? Same happened here as well. So এখানে হচ্ছে there must be a Coulomb's constant, right? So F equals to a very original like symbol used for Zora, K, which makes it very confusing for us because there are like 3 constants of K in your syllabus. Okay, we already did one in the gas laws. It's here. You'll have another one in your astrophysics. Okay, so right, so K, Q1, Q2 divided by D square. Luckily, this constant is wrong. So we can avoid it. So the reason why it was wrong was because, and this is something gravitational field link করা যাবে. In gravitational field, we learned that the capital G, 6.67 into 10 to the power minus 11, right? It's called the universal gravitational constant. What does that mean? Regardless of where you are in the universe, that constant is always a constant. At the edge of a black hole, to the vast, you know, openness of your space, wherever you go, G is the same. Change করার কোনো scope নাই. This K is not constant. It changes. It changes based on where you are. It changes whether you're in air, you're in vacuum, you're underwater, it's in an oil. It keeps changing. So that means the constant is not constant anymore. So the constant has its own formula now. So the formula for Coulomb's constant, K, is 1 by 4 pi epsilon. So this is the symbol for your, so epsilon to explain করতেছি, but this is the formula for your Coulomb's law. In our A2, we don't deal with the epsilon as an open value. We use epsilon naught. Epsilon naught is for vacuum. So that means all the math we do in our syllabus is based on charges where in vacuum. Okay, our epsilon, so I'll write down all the values and everything here. So 4 pi to 4 pi. This epsilon is a quantity in physics. It is called the permittivity of free space. It has a companion equation called mu naught, which is called the permeability of free space. Okay, so yeah, it's just names. About them, but you have to know one thing though, that it makes a difference. Okay, so এটা যদি হচ্ছে epsilon naught এর জায়গায় epsilon a হয়, epsilon x হয়, different material এর জন্য different values থাকে. Okay, so আমাদের syllabus এর মধ্যে we only deal with your vacuum, so our epsilon naught value is fixed. Okay, so yeah, epsilon naught তোমরা ক্যালকুলেটরে খুঁজে পাবা, constant দেখো তো epsilon naught কত দেয়, তাহলে আমরা k টা এখন derive করব. So k is going to be 1 divided by, calculator থাকে এটা 6 maybe, I don't know, সব calculator same না, 32, okay, 32. So slider. constant. How do you bring constant here? Shift 7. Oh, না না এই ভ্যালু দিয়ে দিবে তোমাদের কোয়েশ্চেন পেপারের মধ্যে থাকবে। সো বাট তোমাদের কেসিং নিতে দেয় না এক্সামে? সেটাই তো তোমরা বলে দিবা যেগুলো তো আমাদেরকে দেই দেয় -12, right? So দেখো কে কি আসে। I'm gonna get on to something, so ভ্যালুটা বললে I can tell you what's going on here. It should be 8.8. No, K, which is also in your calculator, I believe. Yes, it is 8.99 into 10 to the power 9. এটা হচ্ছে Newton meter square per coulomb square. Why did I bring this up? It's because it's strikingly different from your gravitational constant. The gravitational constant was 10 to the power -11, and this is 10 to the power 9, which makes it a very strong force. So gravitation, by the way, is the weakest force in the universe, right? Electric field and electric forces are quite strong. Because the constant is very large. Look at that, 10 to the power 9. Strong nuclear force. So yeah, this is the one that brings protons and neutrons together. So yeah, this is the Coulomb's constant. So the exam what I found is that you can use K, but in a Mars scheme they keep using the full thing. So the formula according to our syllabus for Coulomb's law is F equals to Q1 Q2 divided by 4 pi epsilon naught d squared. Okay, so don't get surprised if you see this as basically that formula and the other one joined together. Okay, so yeah, there you go. This is the Coulomb's law. Now, do you guys recall that I gave you in gravitational field that all the forces values have a negative sign in front? F equals to minus gmm by d square. Does anyone remember the significance of the negative sign? Yeah, attraction. Potential. So the negative sign represents attraction. এখানে কি হবে? Should it be plus or should it be minus? Should it be both? It'll be both, right? So both কেন? Because আমার যদি হচ্ছে এটা plus হয়, it means there is what happening? Repulsion. আর যদি minus হয়, what does that mean? Attraction. Okay, so plus means, so if you do a math and you get a positive value, it means it's repulsion. And if you do your math and if you get a negative value, it means that there's a what force here? Attraction. So yeah, this is the Coulomb's law, and the formula is here. To copy it, I'll give you the definition as well. So for the definition, you can just directly write the formula, but there's also like a definition on its own. Could atoms be shaped like? Yeah, of course. And you as well. If they had different masses with same charge, what would happen? They'll move differently because the smaller mass will move easily compared to the bigger mass. We take the distance of separation between the center of the charges because we have point charges. It means you take it from the point to the point. If you have different masses, so for example, this is 4m and this is m, right? It'll look something like this. because the 4M wouldn't move a lot, but the small m for the same force will move very easily. So if you have different masses, the lighter one moves more compared to the bigger one. It's creepy. The uncanny valley. That makes it even worse. I don't know what its emotions are. There's a robot from this company called Boston Dynamics. They make like fighting robots. Yeah, I'm scared of that. No, it's actual. Yes, it has already done. Like my friends who are in computer science, right? They just keep talking to AI all day. Nothing else. There's like continuous chat with it. Yes, it's actually true. Like it'll assist the person, but there are a lot of people right now who are just doing math. Like calculator কাজ করতেছে, computer science ওদেরকে replace করে দেবে. But the people who decide what math to be done, ওটা তো replace করা যাবে না. So ওইটার জন্য you still need computer science engineers. But the coders, right? Or the so the nature is different. Yeah, and they killed it. কারণ ওরাই তো কোড করে বানাইছে এটাকে. No, so they made a prediction in the next 20 years, all the creative jobs out there, they will peak. Because if you have ever seen AI do like, art, right? It's not that good. Yeah, so it's the creativity that will become very important. So, writing, arts, filmmaking, those kind of jobs. Yeah. Oh, that would be good. No, I used to play this game called Dota 2, like AI bots. Crazy. When they know before me what I'm gonna do. I don't know how they predicted what I'm thinking. Yeah, I used to play it. What about what is that? Some engineering will disappear. I think electrical engineering will entirely disappear because the jobs that electrical engineers right now do, for instance, right, they will set up a network grid. Bangladesh's the electrical grid আছে ওটাকে set up করবে, ওটাকে maximize করবে efficiency, ওটাকে control করবে. Bangladesh itself shifted to a computer software like 5 years back. Which there were like a couple of days software crash করছিল. So we are already using like software to do that, right? Yeah, so already in USA the whole grid runs on computers. Computer does that. Like কোথায় load লাগবে না ওগুলো সব হচ্ছে computer does that. It used to be done by engineers before. So yeah, that job will go away. এগুলো চলে যাবে, এগুলো AI আরো better করে. I mean the stock market হচ্ছে AI based traders, right, are outwinning everyone. So eventually computers put bets every day সকালবেলায় stock market. So computers can do it way easily. They process 1 trillion data per second. A person to click করতে পারে না so আরো নিজে কিনে ফেলে এখন the high end funds out there, the bots buy themselves. So they get টাকা দিয়ে দেয়, they just buy and sell. Okay, so let's move on. So this is the Coulomb's law. Do you have any question regarding the Coulomb's law? Okay, next is before we move on, actually need to clarify just like gravitational field, right? The gravitational force is not that useful. Do you remember why? What was the limitation of the gravitational force? Like in the chapter, right? F equals to g mm by d square, right? What was the limitation of that? No, there was a reason we found the formula, but we realized the formula was not that helpful, and then we came up with a new equation. Yes. So gravitational force F equals to gmm by d square basically tells you the interaction between two masses. But what if I have just like a random mass out there, and I want to know the strength of that mass and its field around it? তখন তো force দিয়ে কাজ হচ্ছে না. So we came up with a quantity that's much more superior. What was it? Gravitational field strength, the small g, right? Similarly, এখানেও the force is not really that helpful unless you have two charges and they're interacting. What if I have one charge and I want to know how the field around it looks like? So again, what will we have here? Electric field strength, right? And just quick reminder, what was the formula for electric field strength? My last 3 classes very good to see. E equals to electric field strength equals to V by D, but what is the original formula? F by Q, right? So we already know what our force is here, and we know it's going to act on a charge, right? So key hobe K Q1 Q2 divided by D square on a charge. So the charge cancels out, and you get electric field strength for a non-uniform field to be what? KQ divided by D square. Isn't it very similar to gravitational field strength, which was what? GM by D square. Okay, so they're very similar. The parallels on power. So again, gravitational field strength advantage you could use multiple field strengths and find out the net effect at a point. If I have a plus charge here, minus charge here, plus charge here, and I want to know what's happening here, what will I do? I'll find the strength of this at this location. I'll find the strength of that at that location. I'll find the strength of that at that location. And because it's a vector, what do? I combine them. And you might have to use vector diagram. Okay, the vector diagram in triangles and everything. So maybe this vector is this way, that vector is that way, and that vector is that way, right? You need to create like a diagram and figure out the result there. Okay, so yeah, that is what we'll be doing next. So the electric field strength and the potential. Right, so after like a chapter, you can say back capacitors. Okay, so if you're doing capacitors, yeah. But it'll be more catered towards someone who already has some knowledge about it. Have you done capacitors in school? Okay. I'll record it just in case anyone. Yeah, school exam review. Right, Paulo, how can I help? Will you do the chapter later? Yes, definitely. I'll do it maybe at the end of this month, or sorry, the start of next month. Capacitors are next chapters. Okay. So yeah, you need help with capacitors, or which topic? Capacitors. Okay. If it's just capacitors, nothing to worry. It's a very small chapter, and I think you also have electric field, uniform, non-uniform, and everything. I need 6 more classes. So by whole electric field, I mean with capacitors as well, right? Just electric field. Oh, that will be done by today's Wednesday, right? Monday maybe. Monday is 28th. Your test is on 29th. So yeah, the majority of stuff I'll be doing next class, and after that the potential we'll be doing later. What I'll do is, I know that the trouble that students have in this chapter is in the graphs. So I have like a document that has all the graphs in it, like all the graphs from this chapter. I'll just upload that for you guys. You can go through that. Right. So capacitors. Let's see.
Recording in progress.
Okay, so chapter 19, capacitors. What are you supposed to know? So you need to know the basics of what capacitors are, because it's a completely new topic. We haven't done it before. You need to know how does it store energy, and you need to know discharge equations. So there are these exponential equations that we need to learn. So what is a capacitor actually? So before we start, we need to understand what is a battery. So a typical battery, right? What does it do? It takes in chemical. So there's a chemical inside this. This one is lead acid, right? And a chemical reaction takes place. And that chemical reaction causes the chemical energy to be transferred to what energy? Electrical energy. That's what a battery does, right? Capacitor is very similar. What a capacitor does is that it doesn't have its own energy source. It takes energy from a battery. So what's the design of a capacitor, first of all? So a capacitor consists of two parallel plates here. And this should ring a bell for you, because two parallel plates is also what is there in a what field? Uniform field, electric field, right? So there's a uniform electric field generated in between. You place two parallel plates next to each other, right? So what happens is you take your capacitor, this device. It looks like this, by the way, this real life. It's one of the most commonly used components in electricity. You'll find like every appliance board, there are these out there. We are not going to do that one. We'll be doing these. These are parallel plate capacitor. The cylindrical capacitors are a little complicated. We don't have that in our syllabus. They look like this. So they're basically wrapped around like that, okay? So how does a capacitor work? The most basic version of it. So you take a battery and you connect it to a capacitor. This is the positive terminal of your battery. This is the negative terminal of your battery. What will happen is that the positive terminal here will attract electrons out of that plate, and the electrons will go like this to the battery like that. Also, the negative terminal will what electrons here? Repel them, and the electrons will go like that, and they'll get stored there. So what happens eventually is that on this side of the capacitor, you have a lot of electrons, and on this side of the capacitor, you have fewer electrons. And as these electrons go from the battery all the way up to the capacitor, what do they carry from the battery to the capacitor? Energy. It's basically like this, okay? I want to store energy in, let's say, table tennis balls, right? And how can I do that? So what I'm going to do is I'll take a lot of table tennis balls, I'll raise them up to like a height, and I'll just keep them there. And when I want the energy back, what I'll do is I'll release them, and they'll fall. So the process by which I take the ball to the height with my hand is basically done by what here? The battery. So the battery pushes the charges to the capacitor, and the capacitor will hold the charge, and it holds what within the charge? Energy. And then what I do is I will take this capacitor, which has stored charge and energy, and I'll connect it to a lamp right now instead of a battery. And once I connect it to a lamp, previously the charges couldn't go that place, because this is negatively charged, this is positively charged, and they couldn't go that way either because there's a negative terminal there. But the moment you remove the battery and place a lamp here, what will happen is all these charges that were very eager to go that way, they couldn't, because what's in between? A gap. They'll start to go the other way, and they'll go like this, and they'll go like that, and they'll go to that place. When they go the other way, what do they travel through? A lamp, right? So they lose all their energy to the lamp, and the lamp then glows. So what did the capacitor do here? A capacitor is a temporary hold of electrical energy. It's a temporary place to hold it. Then students start asking a question, why? I mean, I could just have used a what instead, a battery, right? Why do I take the energy from a battery, hold it somewhere, and then use that held energy to run an appliance? Wouldn't it be easier to just directly run it like that, right? So why do they do that? So it turns out capacitors have quite a lot of special abilities. One of them is that they can understand the concept of time. So you can actually time how much time would be needed to turn on and off your appliance. With a battery, you can't do that. So if I connect a battery to a lamp here, right? How does a lamp glow? Brightly. And then over time, the battery starts to drain out. And what does your lamp do? Die out, right? If I use a capacitor, I can actually control the amount of time it stays on, and I can shut it off, right? It's also used in a process called smoothing. it's used in your fans. We will do that in a later chapter, where you can convert an AC supply to a DC supply. Okay, so that's the basic background to a capacitor. Capacitor symbol is this one, two parallel lines like that. The symbol in terms of word is capital C, and the unit for capacitance is farads, capital F. Capacitors usually come in very small values, like nano, pico, micro. Okay, so I'll show you an animation. This one makes capacitors much easier to understand. So here, see what I'm going to do with a capacitor right now. So on the left hand side, I have a battery. On the right hand side, I have a bulb. So what I'll do right now is I have plates like this, which I can move. I have plates that I can make bigger and smaller, right? So I'll bring the plates like this, and I'll turn on the battery. As I turn on the battery, do you see that the plates became charged? So there's a positive charge plate on the top and a negative charge plate at the bottom, right? Now, I can move this switch here, and this process that I just did here, this process is called charging the capacitor. So the capacitor is charged right now. I'll remove it from the battery, and then I'll connect my charged capacitor to the bulb. See what happens. Do you see how it's slowly dying off like that? This is the discharge of a capacitor. So whenever you charge a capacitor, right, you give it energy. When you discharge it, it gives the energy out. Why would we do that? Because we can control the time it takes for the lamp to glow. I'll give you an example right now, which is, let's say I take the plates very far away and I make it very small like that. Do you think the lamp will glow for a longer duration or a shorter duration? Compared to before, right? This was the previous one. See what happens. You see it's glowing over very long duration. Why is that so? Because the plates have a lot of what on them? Charge. So wouldn't it take a lot of time to discharge them, right? On the other hand, what if I make my plates very small and I take them very far away? Do you think that this will glow for a long time or a very short time? Let's see. Why? Because there's so few charges out there, they get discharged almost instantly. So this is an advantage with capacitors. You can actually control the amount of time it takes for the light to glow. And what you're seeing right now happens in a car. So inside the car, there's a light, cabin light. So when you close the door, some cars, you'll notice it dims down. It doesn't turn off. That's done using a capacitor. Okay? Because if I just had a normal lamp, right, what would it be? On or off? But a dimmer will make the light slowly glow down and stop, right? And you can control this. But you might be wondering, that on its own is not a very useful application, right? So where else do we use it? All the timers that you ever seen in any appliance, right? They use capacitors, like oven timer. In the oven you have 10 minutes, 15 minutes. What are you actually doing when you move the knob? You're actually changing the capacitance. And the higher the capacitance you have, the longer the oven will work, and there's a countdown that shows up, right? And if you want to reduce the time your oven is going to work, you change the knob to 1 second or 10 seconds. You're basically changing the property of the capacitor inside, and it shuts down very rapidly. Okay, so let me show you. So imagine this is like that, right? And if I bring the plates closer, do you see more charges show up? And if I take them further away, do you see charges go away? So why is there more charge showing up when you bring the plates closer? The reason behind that is the closer the plates get, the more repulsion they experience and the more attraction they experience. So you can push out more charge and you can pull in more charge. But if the plates are very far apart, there's not really a lot of interaction between them. So therefore, they don't store enough charge. Okay. So yeah, this is the very basic version of a capacitor. Okay, I mean, I'm trying to go through the other parts quickly. One more time, capacitor is a device that's used to store charge or energy. It's the question they'll ask you. Capacitors store energy using what within them? Charge. So the charge is not actually stored. The charge is already there. What are you doing in a capacitor? You're basically taking the charge that's already there and separating them. So you're taking the plus away and putting the minus in. But if you look at the total charge in a capacitor, what is it all the time? Same. There's no new charge added or charge removed. But as the charges go to a higher potential, what do they store? Energy. And when you let go of them, they'll fall from the higher to the lower part and they'll give out the energy. There's an analogy for this. When I'll be doing the chapter, I'll show you many analogies. But the most famous one is water and a dam. So imagine you have a dam, right? And you have water in the river. And what you do is you use a pump to pump the water up to the dam. So the what's stored in the dam right now, GP. And let's say later on you want to use the water for electricity. What do? You let the water flow. As the water flows, what does it give you back? Electricity. So the charging process is taking the water up to the dam. The discharging process is the water being released. So that's the same thing happening here. Okay. Right. So that's the introduction to capacitors. Now, what's the formula for a capacitor? So let's see that. So what's an equation for your capacitors? So the equation for capacitors, there are three of them that you need to know. The first one is this one. It's the most important one. Q equals to CV, or C equals to Q by V. Okay, so what is Q here? The amount of charge stored in your capacitor. What is V here? The potential difference between the plates of the capacitor. And what is C? The capacitance, right? And how do we find that value? So when you have a capacitor, right, and you're charging the capacitor, what we find is that this is 10 volts, let's say. And initially, uncharged capacitor has what voltage across it? 0, because what's not there on the capacitor? Any voltage, any charge, right? 0 volts. As the charges start to move here and they start to build up here, what will you start to notice on the capacitor voltmeter? The voltage is increasing. So it'll go like 0, 1, 2, 3, 4, 5, 6. What's the maximum value that it can reach? 10. Why? Right, very good. But why not stop at 9? Okay, so the reason is the sole reason why charges actually flow from here to there is because there is what between the two things? Potential difference. If you remember from O levels in electricity, there's something called potential difference. So let's say there's a battery here with 5 volts. I put a battery there with 5 volts as well, facing the opposite direction. Nothing happens. Why? Because there's no potential difference. But if I put a 5 here and a 10 here, it will be like that. And the charge will flow from where to where? The higher potential to the lower potential. So in a capacitor, what happens is it starts at 10. This is the battery. Okay. What's the voltage of the capacitor at the start? 0. So a lot of charge will flow, right? See something very interesting here. Do you think if I release a ball here, would the ball move very fast or slow? Fast, right? Now, this is 10, this is 0. This charged a little bit. It became 3. Do you think the ball will still roll? Yes, but will it be as fast as before? No. So the rate decreases and it keeps increasing. So the rate keeps decreasing. And at one point, both become same. What happens to the rate of charge flow? 0. And that is a very important concept in your topic. It's called the discharge graph. So I'll show you what the graph is, the 3 graphs that you have. Okay. So you find that initially the rate of discharge is very large. And as time passes by, what happens to the rate of discharge? It decreases. And you understand why? Because what is decreasing? The potential difference. Okay. So the graph for current, charge, and voltage for discharging is the same. And this is our second equation that we need to know. Very, very important equation. I equals to I naught e to the power T by RC. So what is I? That's the current in your capacitor or circuit. What's I naught? The initial current. What is T? The time that's taken. What is R? The resistance of the circuit. What is C? The capacitance. So what's the purpose of this equation? So let's say you have a capacitor that is discharging right now, and you want to know the current at any given time. What would you do? That equation. What if you want to know what's the voltage at any given time? That equation. What if you want to know how much charge is left in the capacitor at a random given time? That is the equation. Okay, so it's called a transient equation. It basically tells you the amount of charge, current, or voltage at a particular given time. Okay. Never 0. Why? That's a good question. So the reason why it's never 0 is because here. So do you see that I'm trying to charge my capacitor right now? And during the charging process, what happens is electrons are pushed like that, and the electrons move here and they start to store there. And at the start, when I started my whole process, right, was there any electron displayed? No. So the first electron that came out had like a free highway to move through. So it went really fast to that location. But the second electron that's making its way there, will it find it as easy as the first one, or a little difficult? Little difficult, right? Why? Because isn't there already a negative charge out there? And aren't you going towards a negative charge? You being negative charge will prevent you feel repulsion. So it slows down a little bit. And then as you keep adding more charges here, more charges are developing here, the subsequent electrons that are moving in, right, will start to feel what? More and more repulsion. Now imagine, of all the electrons available, 99.9% of them are here, like almost all of it. And this one last electron is left. Do you think that electron will find it easy or very, very difficult? Very difficult, right? But it will try, and it will take a very long time to eventually overcome the repulsion and get there. Mathematically, it will take infinitely long. That's why the graph never touches the x-axis. It's an asymptote. Right, so Q equals to CV, and if you want to know the amount of energy stored in the capacitor, we have these three equations out there. So let's say you're given a capacitor and they're asking you how much energy is stored inside it. These are the equations: half QV, half CV square, half Q square by C. Interestingly, capacitors have a counterpart that you've done before, with same equation, same concept. Could be strange at the counterpart, and I think some students find it easier to remember that way. Do you remember any energy equation that was like half something something from your AS? Yeah. No, that's half mv square, right? But just half something into something. No. Energy formula. Think of an energy formula that's half one quantity. Yes. Springs. Capacitors and springs are surprisingly very similar. The way they behave, the way they combine. And why am I saying this? Because you have a chapter in your syllabus which is called combination of capacitors, and combination of capacitor equations are exactly the same equations for combination of what? Springs. So if you can remember springs, you can remember this as well. So what does it mean? So let's say you want to combine capacitors, like two capacitors in series, right? How would you find the total capacitance here? It's 1 by C total equals to 1 by C1 plus C2. What if your capacitors are in parallel? How would you combine them? A C total equals to C1 plus C2. So there's a derivation, obviously. So how did I derive this? Let's see. See, if I'm given a voltage V total here, the voltage will be what between the two capacitors, just like resistors, shared, right? So my V total should be equal to what? V1 plus V2. Do you recall this? Like potential divider rule. Now, what's Q equals to? CV. So V should be equal to what? Q by C. So you have your Q by C here. But something very important, if 10 electrons come here and deposit themselves here, how many electrons will move out from here? 10. Show what I said. If 10 electrons come here and deposit themselves here, how many electrons will move out from here? 10. And 10 electrons will go there. And if 10 electrons go there, how many electrons will move out from here? 10. And the 10 electrons will come back here. So in a series circuit, just like in our resistor topic, what is same for both the resistors in series? Current. What is the same for both the capacitors here? Charge. So the charge here and the charge here is same. And the charge here is also same because it's, transferred everywhere. So the charges are same. Wouldn't I be able to cancel all these charges out? So therefore, what do I have? This one here. And in parallel circuit, just like series, resistors, in parallel circuit, what is same for both the capacitor? Voltage, right? But what gets divided here? Charge. How does the charge get divided? Based on intuition, tell me. Will more charge go to the place that's a bigger capacitor, or less charge go to the place that's a bigger capacitor? So I have a pipe bringing in water, and it goes to two separate pipes. There's a small container, there's a big container. Where will you have more water? Okay, so in this case, no, so it's actually opposite. So Q goes to CV, right? And if my voltage is constant, the more the capacitance you have, the more what can you store? Charge. In resistor is different because resistor actually hinders your what? The flow, right? So higher resistance would mean less stuff can flow. Higher capacitance is basically welcoming more particles in. So more capacitance means more charge. So yeah, if that's the case, you'll find that voltage is same, and you combine and you get this. But keep that in mind because it'll be needed later on. That more capacitance means more charge. Okay, right. So and then these are not there in your paper. I haven't seen them for some time. The syllabus has changed a little bit, but capacitor combination questions. Okay, they work the same way as you solve what question? Resistor combination. So if I wanted to find the total charge here, what will I first do? Combine these two, and then combine those two, and combine these two, and then I'll get my total capacitance. I know my total voltage. That'll give me my total charge. Okay. Right. So that is the other thing about capacitors. And lastly, that. What is this? Tau. What is tau? Right. Do you know what time constant is? Okay. So Amboli, what's this? This is interesting. It's actually, remember radioactive decay, half-life calculation? It's actually related to that. So turns out when your capacitor is discharging, again, strangely, it follows the same decay equation of a radioactive decay. Remember radioactive decay? And in radioactive decay, we learned something, that there was actually a time that was constant throughout. It was called the half-life. What was that time? Time taken for the original activity to become half the value. So it keeps becoming half, right? So in this particular scenario, you have current, right? And the current is going down, down like that. We find that there's something constant here. The time taken for your current to become a certain value is always the same. What is that value? It's too difficult to say, but easy to understand. 1 by E, the original value. So in a calculator, there's a constant E, right? So if your current is initially 1, the time taken for current to become 1 by E is always going to be the same. For the time taken for it to be 1 by E square, for the time taken for it to be 1 by E to the power 3. What I mean by that is, I'll put it on the graph here. These intervals that you see here, they're all what? Equal. How much change has taken place in each scenario for these time to be equal? The values have gone down by a fraction of how much? 1 by E. In radioactivity, it wasn't 1 by E. What was it? Half. So this probably would have been termed the E life if it was the the right way of saying it. But if that's the half-life, this is the E life. Let's see if it makes sense. So what's half-life? Time taken for it to become half the initial value. What's this thing? It's the time taken for it to become 1 by E the initial value. But they had a better name. They call it a time constant. Okay. So time constant is it's tau, TAU, and this is equal to R into C. So that time is always the product of the resistance and the capacitance. Okay, so that is it. And so yeah, the RC value here, RC value here, these are all RC, which is the time taken for them to become 1 by E. The capacitor with more capacitance will get less of the voltage in series circuit. Yes, that's correct. Actually, I forgot to mention. In the series circuit, remember this combination? The one with higher capacitance will actually have less voltage. Why? Q equals to CV, V equals to Q by C. What's the relationship between V and C? Inverse. So the one that's with a higher capacitance will actually have less potential across it because the charges are actually spread out. So therefore, there's not enough potential developed there. Okay. And that's more or less it, actually. I'll solve a question for you guys to see tomorrow. It's not a very common topic, capacitors. Right, before I show you a question, do you have any questions from capacitor that you remember, something you have done in school that you didn't understand? What do you mean? It's not done yet, the chapter? Oh, it is done. Okay, let's try this. That's a good question. So a capacitor, a battery of EMF 12 volts is and a resistor of R is connected in a two-way circuit. Do you understand what the two-way circuit is? Is that example I showed at the start, the animation, right? So two-way is basically you can charge, discharge, right? The switch is initially in the position S and the capacitor is fully charged. So capacitor gets fully charged here. Can anyone tell me what evidence gives you the idea that it's fully charged? Like, how would you know it's fully charged? Because you can't see it charge it, right? So how do you know it's fully charged? It takes time to charge. So how would you know that my capacitor has been fully charged right now? No. But like, practically speaking, you have a capacitor that's charged, right? How do you know it's fully charged? It doesn't have like a percentage on it or anything, right? Potential difference would be close to zero. Potential difference of what? Yes, correct. Or you could just say that the battery's voltage would be the same as the voltage of the capacitor. Okay, so the way we do this is we take our voltmeter, we connect it here, and this is 12 volts, right? So this will keep going up, and when it becomes 12 volts, you know it's fully charged. Okay, so yeah, that's how you know it's fully charged. Now it says that it's moved to T, and then as time goes by, it discharges. There's the graph given here for LNQ versus T. What is this LNQ graph here? So it's something we'll learn in a chapter later on, radioactivity, but buchhai jinishta. You can convert, this is not physics, it's math. You can convert any curve into a straight line. It's called the linear log. Have you heard of it? So if my discharge equation is Q equals to Q naught e to the power minus T by RC, and the outcome is like a curve, convert this for me to a straight line. What would I do? I will take natural logarithm on both sides, okay? So ln Q is equal to ln Q naught plus ln e to the power minus T by RC, because when it's multiplied in terms of log, it gets added, okay? Now, what's natural logarithm base E? 1. So therefore, ln Q is equal to ln Q naught minus T by RC. And if I take this as my y-axis, and if I take T as my x-axis, then I get y equals to mx plus c. C will be ln Q naught. My x is going to be what here? T. And what is my m going to be? The gradient of the graph? 1 by RC, minus 1 by RC, yes. Do you see that the graph has a negative gradient? The gradient of this graph is actually what? Minus 1 by RC. So, yeah, minus 1 by tau. Okay, so the gradient of this graph is, I don't know what the question will be later on, but let's just break this down. Gradient is going to be minus 1 by RC. And this intercept here is what? ln Q naught. Okay, so if you want to know the initial charge stored in your capacitor, what will you do? You'll use this value. If you want to know the resistance or capacitance or anything related to that, what do you need to find? The gradient. Okay, let's see what they want here. Show that the capacitance is 1.5 microfarad. Do we know the resistance? Resistance is R. This is discharges. Show that the okay, it doesn't matter. I think there are other ways of doing this. So can you tell me how to find the capacitance of the capacitor here? We want to find C. What can I do here? Gradient, but the gradient will give me minus 1 by RC, right? What's R? So how can I find the value of C without knowing R? Q by V. Yes. How do you find the V? The V is 12. How do you find the original Q? Yes, correct. Very good. So what's this value here? 2.1, 2, 3, 4, 5, 6, 7, 8, 9. 2.9, right? And don't forget what's here as well, micro. So your ln Q naught is equal to 2.9. So therefore, Q naught is going to be e to the power 2.9. Can you check what the value is? 18.17. So it's going to be 18.17 into 10 to the power minus 6. Do you know why? Because what was the coefficient here? Micro, right? So you have to bring it back. So I know my watt charge here, initial charge. Now we know that there's a formula for capacitance. What is that? Q equals to CV. If you use the initial charge, you have to use the initial voltage. When the capacitor was fully charged, what was the voltage? 12. 12 volts. So therefore, 18.17 into 10 to the power minus 6 equals to C times voltage is 12. That will give you a value of C. Can you check what this is? Right. So that is how you find it. Is it clear? Okay. Now find the value of R. That's going to be easy. What do you need to find here first? The gradient. Okay. So gradient of Bayes curve, and the gradient is going to be equal to minus 1 by RC. We already know C, so we just need to find the value of R. Calculate the energy stored in the capacitor at time equals to 0. So energy stored has three formulas: half QV, half CV square, or half Q square by C. Depending on what your requirement is, you use. So in this case, we do know Q and V, so I can just use one of those, right? So these are the equations for energy stored in a capacitor. Okay. Yes, it's area. So the graph for a capacitor being charged is going to be this straight line for Q versus V. So if I want to find the energy stored, I need to find the what of this graph, the area under the graph, which is half QV. Let's see what's going on here. A second identical resistor is now connected in parallel to R. So we are placing a second identical resistor here parallel to R. And what happens next? The switch is initially at S, the capacitor is fully charged, the switch is moved to T, so the capacitor discharged, basically repeating the same thing as before. At time T, the switch is moved like that. On figure 5.2, sketch a line to show the variation of this. Yeah, so basically they're asking you how would this line look like if you had how many resistors up there? Two of them, but in what combination? Parallel. What do you think? Would it be starting from a different location, or would it start from the same location? So the answer is it'll start from the same location because you're using the same capacitor with the same battery. So shouldn't it store the same charge? মানে Q equals to CV এর মধ্যে আমার C টা কিন্তু 1.5, আমার V টা কত 12. So shouldn't the Q be the same? So it starts from the same place. But do you think the gradient will be the same? What do you think will happen to the gradient? The gradient is minus 1 by RC, where R is what? The total resistance, right? We now have two resistors in parallel. Yes, because when two resistors in parallel like that, right, what happens to the net gradient? Halves. Remember? And as the gradient halves, net gradient, net resistance. The net resistance halves, so the total gradient doubles. So it's going to be like this. And they're very adamant about this, that you have to be very careful about the value. So let's see how to figure that out. So it crosses which location here? 1.6 maybe, 6. So it's going to be half of that, 0.8. So this line must be crossing 0.8 like that. So you have to be careful about where it goes through, not just a random line. Okay. Yes, this is actually a very good question. Not an easy one. You get much more easier. Also not that difficult. There are some complicated ones out there as well. We're using the equation. So this one uses everything that we have seen so far. So that kind of question is going to Do you have magnetism in your exam? And you have every other chapter from before. Ideal gases. Achha. I just wanted to clarify something. I took a test on ideal gases, right? Recently, there were quite a few number of questions on Brownian motion, right? So Brownian motion in the new syllabus has been retracted. It's there, but it's not as much as before. In the previous syllabus, you had like demonstrations, use a microscope to see how Brownian motion takes place. I later realized a couple of questions came like that. So don't worry about it. All you need to know is this one. So the one we have done. So what's Brownian motion? Or why do we need Brownian motion suddenly in our A levels? So there was this thing that I showed you at the start of the gas law topic that we make some assumptions. Do you remember? Here. Okay. So there, number 2 point, particles undergo random zigzag continuous motion. This is justified by the idea that particles have kinetic energy and they're bombarding with each other at all times. Proven by experiment. That is the Brownian motion experiment. Okay. So that's all you need to know. Nothing much. I was like going to the textbook as well. They actually removed the petri dish example with pollen grains moving around. So we don't have that anymore. But in the past paper, I think there were questions before. Now you don't have them. Yeah, in O levels, you had one with a microscope and a smoke cell, and you look into it, basically that.
Recording stopped.
I'll upload this. You can just go through this if you need again. And we have one more class on Saturday. I'll be doing electric fields there. So if you have anything advanced of electric fields that I haven't done any problem with, you can ask me that day. Okay, Saturday.